I need to finish 10 to 8, yeah, 10 minutes here.
Yeah, sure. So in measure phase yesterday, we have discussed that there will be few inputs for the measure phase. There is a process that we need to follow, and there will be outputs. What are the few of the inputs that we have discussed? We have discussed that project charter would be an input, critical customer requirements would be an input, and high level map would be another input. Then measure phase is all about ensuring that the measurement system is providing good and reliable data. We collect the data and then establish a baseline for the project. So in this we collect data, establish baseline. And then we have few outputs. What are those outputs? Output is valid measurement system, and then we baseline Y, and also we try to baseline the statistics. We also come up with a detailed process map. These are few of the outputs. Then we have also discussed about performance standard metrics. We need to come up with proper performance metric, standard matrix. For the primary metric, which is also called as project Y, we define how we measure the characteristic. What is the definition of the defect and where the data is obtained from? All these things we calculate. For instance, what is the item, what is the metric, what is the opportunity data type, so on and so forth. Then first choice is to look for data that is already collected. Next thing is you need to actually have the data to baseline. So in data collection, we actually look into data that already exists. And if not, only then we'll go for collection or survey or questionnaire. Then we have also discussed about measurement system analysis, MSA. Here we discuss that measurement value is the sum of true value and measurement error. That means always there might be some error in your measurement. That is nothing but observed variation. The variation that you see in a process is because of true variation and also because of measurement system error. Then true variation is nothing but your actual process variation. It can also be called as actual process variation. But your measurement system variation, let me put it as variation. Has again two types of variations. Variation due to gauge, variation due to operator. These are the two things. Now variation due to gauge, again you can have four types. One is accuracy, which is also called as bias, precision, error, stability, and then linearity. Accuracy is difference between the average of observed values and the standard. Difference between observed values and the standard. Precision is variation observed between repeated measurements or repeated observations. Variation seen between repeated observations. Of the same unit. Then stability and linearity. What is linearity? Linearity is nothing but consistency of measurement system across its entire range. Then comes stability. Stability is variation which occurs with time. Then we have discussed about accuracy versus precision. We have discussed about stability versus linearity. And then we have discussed about something called as discrimination. Discrimination is nothing but the smallest division on the scale of the gauge that you're using, or the smallest difference in reading that can be shown should be 1/10. Right? Your instrument that you're using should be able to measure smaller than 1/10 of the tolerance. One-tenth of the tolerance. And then we have also discussed about calibration and traceability. Calibration is adjusting the output on a measurement system to agree with value of the applied standard. Traceability is an unbroken chain of comparisons with your international or national standards. Then there should be a master gauge. No one should touch that, all that we have discussed. And then we were supposed to actually start the criteria part. So let us get started. All right. How do you classify for a continuous scale? You'll have accuracy, which is nothing but percentage bias or percentage linearity. Then we also measure precision, that is percentage gauge RNR, and then we have resolution. Resolution is number of distinct categories. And this part we have already done accuracy, precision for discrete data, which is nothing but percentage appraisers versus standard, within appraisers or between appraisers, right? These values we are very aware of. When should we accept measurement system and all that. But these things are something, a few things that are new for us. This is not percentage. All right. Percentage bias or percentage linearity should be less than 5% if you want to accept the measurement system. 5 to 10 you cautiously accept, and greater than 10% you reject it. It also has 2%. Okay. For percentage gauge RNR, less than 10% means you accept it. And if it is 10 to 30% in between, you cautiously accept it. If it is greater than 30%, you reject it. Then when it comes to the resolution, these are all various metrics. These things will become clear once we do the exercise. Number of distinct categories. If they are greater than 10, you accept the measurement system. 4 to 10, you cautiously accept, and less than 4, you reject it. So this is an MSA checklist. Before conducting measurement system analysis, it is suggested that the following checklist must be filled. Determine the gauge or the instrument that you want to use. Are there more than one gauges or instruments for the same data? If yes, after MSA, you have to pick that particular instrument which is most suitable. You will have to define the procedure on how you have to take the measurement. Do you have any standards against which you measure your performance? If yes, then are those standards updated? Are they used thoroughly? If the answer is no, plan with the team to come up with some standard. Industry standard, national standard, or international standard. Define the design intent of the gauge or demand from supplier. For instance, discrimination, resolution, granularity, to what extent can you measure? It should be 1/10. If I'm taking the height of people in feet, then my device should be able to take the height readings up to 1/10 of a feet. Then accuracy, how accurate it has to be, how precise it has to be, all those things. Right, let us do RNR study using a case study. This RNR study is used to analyze causes of variation for the data. Collect the data and perform measurements. Analyze those things statistically using RNR study. You judge the results. If required, correct the system and retest to ensure limits of the instrument are acceptable. We primarily have two types of data types. One is discrete and one is continuous. If you have discrete data, you do attribute RNR, the thing that we have done in green belt. If attribute RNR is not possible, then do a logical validation. If the data is continuous, go with gauge RNR, which we'll be doing now, or a logical validation. Logical validation means nothing but I just look at the device and then I make a statement. I do not do any calculations. If calculations are not possible, only then I go with logical validation. Alright, within gauge RNR for continuous data, you have two types of designs. One is crossed design and one is nested design. What do you mean by crossed design? This is part 1, this is part 2, part 3. Some manufacturing, take example of car engine, right? You can take 2 as car doors, 3 as the brakes of the car. Yeah, just assume these are the 3 parts. This is used when each part is subject to repeated measurements. Each part is repeatedly measured. Each part is inspected by each operator. If you take example of operator 1, he measures 1, 2 and 3, everything. The arrows are pointing there. If you take operator 2 also is measuring 1, this one is measuring 2 and is also measuring third one. Yeah, each person is measuring the each part again and again. For example, weight of the drug. I want to weigh the drug. This is what I've done. Then we have nested designs. Nested design means each operator is given different parts, but from the same batch. They're given different parts actually to take the measurements. This is used when the same part cannot be used for repeated measurements, as the parts get destroyed on testing. Look at this. Measuring the effect of a drug by dissolving it in a chemical. Once you dissolve it in a chemical, gone. You cannot once again bring back that and again dissolve it. So you have to come up with a new drug. You have to dissolve it in that chemical. Again, take a new drug, dissolve it. Because after dissolving, you cannot reuse that drug. Hence, operator 1 is given different parts. Right, and operator 2 is given different parts. Same part you cannot do it because it's destroyed. That part will be destroyed. Yep. So continuous gauge RNR approach. Select 3 to 5 parts that span the entire range of variation of the process.
Hello?
Yeah, Anuj?
Bani?
Yeah, Anuj?
Can you hear me?
Yeah, I can.
Yeah, I'm getting it, but I'm not getting it completely manner. So I think I'm waiting for the exercise to come and then maybe the picture will
It will
become
be clear. Absolutely.
Yeah.
Once the exercise, once we do the exercise, things will become very clear to you. I think it's there. Next slide, we have to do it. Yeah.
Okay.
So just wait until then. Just observe whatever you can. Whatever information you can absorb, just absorb it. All right. Select 3 to 5 parts that span the entire range of variation of the process. Parts or samples should be representative of the population. That means I have a population, I have a sample. Right? Ensure that this sample that you're taking is going to represent your population. Don't pick this sample from a different population. It will not work. Okay. Study should be done for all operators who are performing the measurement. Typically, there will be 3 to 5 operators, 3 to 5 parts. Each operator should take at least 3 measurements on each part to check for repeatability. The study should be conducted blind so that operators don't recall prior readings. If they know what reading they have taken the first time, then they're going to ensure that they put the same readings. So it should be blind. They should not know what readings that they are taking. Select neutral part numbers. Don't give any part numbers saying that this is door of the car, these are the brakes of the car, right? This is the engine of the car. Don't name in that way. Give the part numbers 1, 2, 3. They should not even come to know which part reading is what. And then randomize operator measurement of parts rather than measuring in sequence. Randomize is once they take the measurements, put it in a random order. Then you can probably use Minitab and perform the analysis. Oh, this is not required. All right. Here is our example. Gauge RNR. So just read this, Anuj. A company assembles wire connectors. The final wire length is measured in millimeter. It's measured manually by operators. And the tolerance is plus or minus 125 mm. That means I have those limits. Plus 125 mm and minus 125 mm. Measured by the same gauge, same instrument I'm using to measure the wire length. But I'm taking 3 wires and I'm doing the measurements. And also I'm using 3 different operators. Find if the system is acceptable. Yeah. So what I'll do is I'll just send you the file. Gauge RNR. Send this.
I mean my Gmail, yeah?
Yeah, I'll be sending it to your Gmail. Oops, let me open this one or this one. All right, gauge 2. I need to send this file to you.
In the,
Yeah.
in the real life, what the language they will use, or they will use to do the gauge RNR, we need to do it. What is that?
Absolutely.
Like, okay?
In real life, they will not tell, or anyone, no one is going to tell us, because we are Six Sigma consultants. They are assuming that we know all these things, and we ourselves have to do this. Getting me, Anuj? Because they hire you because they do not know. So we have to know
for what purpose we need. Yeah. For what purpose we are doing the gauge RNR? To do what?
So if they are
What
taking
makes us to do this?
if they are taking some measurements in their company, whatever measurements be it, length of the car, width of the car, length of the bike, width of the bike, length of the computer, width of the computer, length of the motherboard, width of the motherboard, length of my mobile phone, breadth of my mobile phone, height of my mobile phone, weight of my mobile phone, whatever be it, any measurement that they are taking, right? You are checking whether they are taking the measurements correctly or not. Are they using the correct device to take the measurements or not? Any measurement on this planet, any product on this planet that is manufactured, anything, right? They will measure somehow. How are they measuring? Are they measuring correctly or not? Is the measurement having some problems because of operators who are taking the measurement? Is there a problem with the measurement because of the measurement device? Or is the data correct? For this reason, you do this. Anything, people might be taking width of the tails of aeroplane, height of the cockpit where the pilot sits.
Yeah, but what my question is,
Huh.
what we are getting after doing this, by doing this?
We will come to know whether the data that you have for further analysis is correct or not.
Okay.
You have to do further analysis. You have to benchmark your performance. Okay, Anuj. So why are we doing this measure actually? Measure phase? Why are we into measure phase? What is measure phase all about? In measure phase, I'm measuring my current performance. Today my son is getting 10th rank in his class. That is as of today. I measured his performance. In the school they measured his performance and they're telling that my son is in 10th position. Hence you take some improvement. You will say that since he's in 10th rank, but I want him to be in the first place, so I'll put him to some private tuitions. Then you put him in the private tuitions. Then he gets rank 1. Then you can say that initially in the measure phase, when I measured his performance, he was at 10th rank. After doing the improvements, after putting him to the tuitions, he got first rank. You have to say, right, suppose someone is going to tell you, Anuj, do Six Sigma project. You'll do the Six Sigma project and you'll say, sir, there is an improvement. They're going to ask you, what improvement? How much did you improve? What will you say? I don't know, sir, because I did not measure the initial performance. Initially, I didn't know where your process was at, but I know that it has improved. No one is going to buy in that particular statement. Instead, if you take the current measurement and say that, sir, as of today, the number of defects are 10. After Six Sigma project, number of defects have reduced to 0. Then people will say, okay, earlier there were 10 defects, now there are 0 defects. Now, first of all, in order to make the statement that there are 10 defects, you need some data, you need some past information. Now, in measure phase, what you're doing is that past information correct or not? Yeah, people who were taking the past measurements, were they taking the measurements correctly or not? Right? Were they using any measurement tape or some measuring instrument to take the measurement? If yes, is that instrument that they are using correct? So you check all those things in your measure phase. That is why we are doing gauge RN. All right. So, okay, there's some disturbance actually. All right, anyways. So you'll have to go to Start, Quality Tools, Gauge Study, Gauge RNR crossed. Why we are doing crossed? Because each operator is measuring each part. Is that clear? Each operator is measuring each part. Part 3 is measured by operator 1, by operator 2 and operator 3. Part 2 is measured by operator 1, 2 and 3. So each part is measured by each operator. Hence you're going with gauge study, gauge RNR study crossed. So let me click on that. What is the part number? It is in column C1. Operator in C2. The measured data is in C3. Then we have to click on options. 6 number of standard deviations. This let it be as is. But here, lower and upper specification limit is 250. It is given in question. It's given that it's plus or minus 125 mm. So 125 mm on both sides, right? 125 plus 125 will be how much? 250. Hence I'm putting 250 here. Did you get, Anuj? How did I get 250 here? Or any doubts? Let me clarify if you have any.
Yes. No, so far okay.
Okay, right? All right. I'll click on OK. And then I'll click on OK once again. Okay, I'm using Minitab 16, I believe. So just look at this particular graph once.
I installed 17. I installed 17.
You installed 17, right? That's okay. That's okay. So just have a look at this. I'll tell you what each thing means. You are also doing parallelly along with me?
No, I'm not. Do you want me to?
No, no, no. There are 2 exercises for you.
Yeah.
You can do it then.
Yeah, I will do it once it's finished.
Yeah. Let me use the highlighter. So this components of variation is the first thing that we are going to discuss. Anuj, you're able to hear me?
Yes, I'm here.
Okay. My system got stuck somehow for strange reasons. 1 second.
Can you hear me?
Yeah, I can hear you. 1 second.
I can see 2 yellow dots in the picture which you only the components of variation highlighted in yellow. After that, we marks are moving.
Okay, fine. Fine, no problem. You can just mute yourself. I'll explain everything clearly.
Yeah.
Okay. Components of variation. We'll discuss this first. So the 3 colors are blue, green, and orange. Blue is percentage. This is the percentage with respect to tolerance. Tolerance is given already. It is plus or minus 125 mm. Then green is percentage with respect to study variation. And this orange color is percentage with respect to contribution or variance. All these things will become clear. Just bear with me. For a good gauge, we expect most of the contribution to the total variation should come from the parts. I mean, total variation should come from the parts, and very minimal, that is less than 30% of the variation should come from gauge RNR. Here is the gauge RNR. Less than 30% of the variation should come from gauge RNR. And most of the variation should come from what? It should come from the parts, this one.
What does it mean and what is the difference?
I'll tell you. There are 3 parts. There are 3 parts, part 3, 2 and 1. Yeah, Anuj, there are 3 parts. Agree with that? The question?
Yes.
Right? So, part 3 versus part 2 versus part 1, the variation should be more in those parts. If at all there is variation should be in the parts. Car window, the measurement reading you will take. Then you will take the measurements of the car door. Then you will take the measurements of the car length. Everything will be different, right? Or will you get the same measurement? Anuj, if I'm giving you 3 options, if I ask you to take the height of your particular mobile phone, length of your mobile phone, and width of your mobile phone, do you think the width and the length of your mobile phone will be the same always?
No, different.
It will be different, right? So there has to be a lot of variation in the length measurements and the width measurements that you are taking. So that is what it means, part to part variation. Different parts will be different. If at all there is any variation should come because of the different parts. Variation should not be because of operators or the measuring equipment. Just because Anuj is taking measurements, he'll take a different reading. Just because Bharani is taking a reading, he'll take a different reading. That should not be the case. That is what this says. This says that gauge RNR, right, this particular entire variance should be less than 30%. Here is a percent. 0, 100, 200, right? Somewhere 30 will be somewhere here. It should have been less than 30. But it is, entire thing is greater than 30. If all three colors are there, interpret the blue color bar. So if you have orange, green and blue, all three appearing, then go with the blue color. If the tolerance has not been specified, if in the question, in the question clearly there is tolerance mentioned, plus or minus 125 mm, right? So let me make this very clear. All right. Suppose this is plus 125 mm and this is minus 125 mm. Plus 125 mm and minus 125 mm. What is the difference between these two? There will be a mean somewhere here. Say mean is 0. From here to here you have 125 and here to here also you have 125. So 125 plus 125 will be what? 250. Alright, so that is what I am discussing about here. Then let me go back to the mini tab. Yeah. So if the tolerance is not mentioned, that 125 plus or minus 125%, then you will not even have this blue bar. If you do not have the blue bar in place, you interpret the results using this green color. Is this clear, Anuj, this chart? This particular thing?
So far it's clear.
Yeah. Let us move to the second part, which is R chart by operator. Let me erase all the reading drawings. All right. We'll be discussing about R chart by operator. This graph is used to find stability of repeated measurements by operators. Graph shows results for each operator who is inspecting. Here we have operator 1, here we have operator 2, and here we have operator 3. If each operator is consistent in measuring the parts, this graph should be close to 0 and it should be in control. So if you see this, here are the values which are within your UCL and LCL. So they are in control. This is also within control. And these are also within control. So the measurement readings are within control. Let us look into the third part, which is nothing but...
Sorry, how you can say it's within control?
Because
what you're looking at.
Do you remember the control charts that we have discussed in Greenbelt?
Yeah.
What does control chart say?
Last. Yeah, it was last.
Yeah, what does control chart say? If your data points are within your control limits, UCL, LCL, these red lines are there, right? If your data points are falling within those limits, your process is considered to be in control.
And our limit is 250, is it? Right?
Look at these control limits here that I have marked.
Yeah.
You're speaking about specification limits. Those things that are given are specification limits. Control limits are calculated based on the data points that you enter. Alright? Specification limits are given by customer. Alright, let us look at the third thing, that is X bar R chart by operator. This depicts the capability to detect different samples. The red control limits indicate the gauge variation or the error. This graph shows average part means. X bar is average. Different part measurements, it takes the mean of that. Since most of the variation should come from the parts, we expect the part means to be bigger than the gauge variation. I'll tell you that. Don't worry for now. It should be bigger than the gauge variation. This means that the operators can discern between different parts. That is, for a good gauge, maximum number of points go outside the control points. If it's a good gauge, if it's a good instrument, then all these points which are within the control should have been outside the limits, outside UCL and LCL, because most of the variation should come from parts. So you should have had points which were outside your UCL and outside LCL, but all the points are within these limits. When it comes to operator, things should be within control. When it comes to different part means, it has to be outside the limits. If you're not understanding, just understand one thing. For this R chart by operator, all the points should be within your control limits. For X bar chart by operator, all the points should be outside the limits. If it's outside, it's good. If it is inside, it's not good here. Here, if it is outside, it is bad. If it's inside, it is good. Opposite. Both are opposite to each other. Then let us look at this. Sample to sample variation is shown here. Part 1, part 2, part 3. What is the variation between these three? For a good gauge, we expect to see consistent values for each part being measured by different operators. If the gauge is good, we expect to see consistent values for each part. We do expect to see different means for different parts. So the means joining the parts should not be horizontal. That means this line that you're seeing should not be a straight line. Okay, this line that you're seeing is not a straight line, right? It is slightly towards, I mean, it's ascending and descending. So it's not a straight line. Yeah, that is response by part. Then let us look into response by operator. It shows the mean of measurements by operators. Each operator measures 3 different parts. So on an average, all the measurements for each operator should be consistent. For a good gauge, we expect to see a horizontal line joining the means. So for this response by part, you should not see a straight line like this, horizontal line. But for response by operator, there has to be a straight line. And the last thing is part operator interaction. This shows how different operators' measurements are, for the same and different sample. Values should be same for the same sample. If I'm taking sample 1, 2 or 3, values should be same for the same sample. That means for 1 it has to be same, for 2 it has to be the same, 3 it has to be the same. For a good gauge, all lines should be on top of each other. So I have this black line, red line and green line, all should be on top of each other. This chart can help identify if there is an interaction between the part and the operator or not. This chart will identify if there is an operator who is not consistent with others. or if there is a part that is hard to measure. We'll identify all these things. So, Anuj, don't worry if you are unable to grasp a few of the things. It will become clear now. Long way to go. It will become clear, don't worry. So let us look at this. We will just complete this and close. Yeah, we will just complete this and close. Okay, look at this. Yeah. So two-way ANOVA table with interaction. You have to look into part operator, this value, P value. If P high, you accept null hypothesis. Is P greater than 0.25? Yes. You have to look into alpha value, that is 0.25, because this is part 2 operator interaction. If you're considering only one value, then it will be 0.05. Just blindly remember this. It should be 0.25 alpha value. If this P value is greater than 0.25, you accept null hypothesis. Null hypothesis says there is no interaction between parts and operator. Okay, we will redo this if you are facing some problem. And then we have two-way ANOVA table without interaction. In without interaction, if the p-value is greater than 0.05, you accept null hypothesis. For operator, if it's greater than 0.05, you accept again null hypothesis. All right. So we will do one thing, Anuj, since we are running out of time. I'll stop here. Tomorrow what we'll do is we'll go through this exercise once again.
Yeah.